Hello everyone. I will present our paper entitled Joint Reconstruction Super-Resolution of Hyperspectral CITES Images. The main scope of this work is hyperspectral imaging, where the task is to acquire a rich spectrum that is not only limited to just RGB data that we usually get using a conventional camera due to the color filtering step. Such spectrum can lay in the visible, infrared, or near-infrared regions, and it is essential for a variety of applications such as in computer graphics, agriculture, and astronomy. To capture multiple spectral bands, we can either use scanning-based devices or snapshot spectrometers, such as CITES in our case. CITES stands for Computed Tomography Imaging Spectrometer, and it can capture a full 3D volume in a single shot. The main component of CITES is a diffractive optical element, or a DOE, which disperses incoming light into multiple tomographic projections. High diffraction orders are basically smeared versions of the latent hyperspectral cube integrated by the sensor along the spatial dimension across multiple angles. An undispersed version of the hyperspectral image called the zero diffraction order lays at the center of the image sensor, and it preserves the spatial information of the latent hyperspectral cube. Our goal is to tackle the reconstruction problem from CITES measurements. Conventional approaches iteratively solve for the latent cube, which is a time-consuming operation, and the resulting image has poor spatial resolution, limited by that of the zero diffraction order. We propose a learning-based approach to produce hyperspectral cubes with higher spatial resolution, exploiting the availability of distinct yet complementarily spatial and spectral information scattered across higher-order projections along with the zeroth-order projection. We introduce Hyperspectral Super-Resolution Network, or HSRN, which not only reconstructs accurate spectral information of the scene, but at the same time it performs spatial super-resolution in a joint framework, all while keeping the computational cost at a minimum, achieving 4 times the resolution of the zero diffraction order and performing the reconstruction in real time. This is made possible via LBP module, which stands for Learned Back Projection, and it produces a coarse rendition, spatial and spectral-wise, of the latent cube. A 3D SPC module, which stands for 3D subpixel convolution, and it produces a high spatial frequency residual for super resolution, and a refinement network. We also include an outermost residual connection between the output and a spatially super resolved zero diffraction order for faster conversions and more stable training. For LBP, we propose to reformulate simple yet effective algorithms used widely in computed tomography-based reconstruction problems, namely the back projection and the filtered back projection. The aim of those operations is to map a lower dimensional signal into high dimensional space by simply repeating said signal in the new dimension and summing up all resulted back projected signals. For example, in CITES, the lower dimensional measurements are the 2D projected sub-images. We want to map such measurements across the spectral dimension, which will be the new dimension in our case. We can approximate the back projection operation, in this case by repeating these projections in the spectral dimension and summing up corresponding spectral slices cropped from each high diffraction order to end up with a rendition of the 3D hyperspectral cube. In LBP, we use a 3D deconvolution layer to learn spatial spectral correlations between scattered information, and instead of summing up spectral slices, we perform multiple 2D deconvolutions in parallel on the output of the previous layer, each with a single output channel. Concatenating the products of such convolutions produces a coarse rendition of the object cube. The key 2 observations that allow for super resolution from CITES sensor image are the following. First, local PSFs that correspond to a given higher diffraction order are slightly different for each projection and for each wavelength. So in addition to the subsampling carried out by the image sensor, aliasing is inevitable, leading to distinct spatial information scattered across all projections. In standard multi-frame super-resolution pipelines, image registration with subpixel accuracy is possible. However, the smearing and the spatial spectral multiplexing in our case makes it harder for us to work with such data. Second, subpixel displacements are observable across object edges, which are in turn preserved along the projection angle of a certain high diffraction orders. For example, horizontal high diffraction orders preserve horizontal edges, and so on. One might argue we need a large number of projections across different angles to cover all possible edge directions. Well, that is true, and we only have a fraction of that information available to us, which further motivates the use of CNNs due to their powerful representation capability. 3D SPC performs processing in low resolution space via multiple 3D deconvolution layers. and then 3D reshuffling operations carried out to produce a super-resolved image residual from the learned low-resolution feature cubes. Our approach outperforms the state-of-the-art, all while being lighter and faster than previous methods. Our network achieves up to 4 times the resolution of the zeroth diffraction order, and it outperforms sequential approaches for image super-resolution. We further highlight the contributions of CETIS beyond the limitations of spatial resolution and compare our approach with those devised for CASI systems, where in this case HSRN is tasked at the same time to perform hyperspectral reconstruction and 4 times spatial super-resolution, and it produces better results than those obtained from CASI measurements. We also train HSRN on real data captured by our CETIS prototype. In this case, the target spatial resolution is twice that of the zeroth diffraction order. Here you can see a sample of a reconstructed image in standard RGB space. To conclude, we have tackled for the first time the spatial resolution problem of CETIS and proposed a joint framework for hyperspectral image reconstruction and spatial super-resolution, and achieved real-time performance with a lightweight network architecture. This concludes our paper presentation. Thank you.